Assalamualaikum warahmatullahi wabarakatuh and good day. In this video, we will discuss example 6.3 which is come from the method of distribution function. So let y1 and y2 denote a random sample of size n equal to 2 from the uniform distribution. Okay, remember uniform distribution on the interval 0, 1. Find the probability density function for u equal with y1 plus y2. Okay, so you can see that you have y1, y2, a random sample of size n equal to 2. Right? And then a function u equal with y1 plus y2. So we want to find the density function for this u. Alright, so the density function for yi, which is each yi, is 1. Y is between 0 and 1. Because what? Because it's a from uniform distribution. Okay, remember when you have uniform distribution function, it will be y 1b minus a, isn't it? This one actually y is between a and b. So that's why when you have 0, 1 here, b minus 0, okay, b minus a, 1 minus 0, you get 1. Alright, so that's why for y1 is this density function, y2 also you have this density function. Okay, therefore we have a random sample of y1, y2 are independent because you have two random sample, okay, uniform each, and it's a independent. And then when it's independent, remember in previous chapter you learned in order to get the joint density function of independent random sample, you will have fy1 times fy2, then you get the same answer here is 1, where your y1 is between 0 and 1 and y2 is between 0 and 1 as well, and 0 elsewhere. Okay, right, next is to find the FU. Okay, in order to find FU, you must understand how to get the region. So the random variables y1, y2 have non-zero density. Okay, because it's a uniform, it's between 0 and 1. Okay, over the unit square. So you can see that your y1 is between 0, 1, y2 is 0, 1. So actually you have this square curve. Okay, square shape. Okay, the first step is to find the point. The first step is to find the points y1, y2 that imply y1 plus y2 less than u. Okay, in order to do this, the easiest way to find this region is to locate the point that divide the region u less than u and u greater than u. Okay, because we have this region square, but we want to see u equal with, we have what just now, u equal with y1 plus y2, isn't it? So we want to see where's the region above the u or below the u. Okay, here this one, u less than u or u greater than u. So this point lies on the line of this one. Okay, y1 plus y2 equal with u. So if you look figure 6.3, okay, you can select arbitrarily, okay, y2 as dependent variable. Okay, we find that the line possesses a slope equal to -1. Okay, and a y2 intercept equal to u. So basically, actually, you can try this one. Let's say you have y1 plus y2 equal to u. So y1, which is u minus y2. So you can see here the intercept is -1. Similar, if you have y2, you will get u minus y1. So the intercept is -1 as well. So that's why you will have this line. Okay, because the intercept is negative, it will be to the right below. Okay, it will be like this. All right. Okay, and the points associated with u less than u are either above or below the line, can be determined by testing point. Okay, because we want to see above or below. Okay, we have this line based on this one. Okay, because we know the -1 intercept, so it will be like this, the line. But then we want to see either the u, okay, the point associated with u either above or below the line, can be testing or can be determined by testing a point. So how is it? Okay, let's say u is equal 1.5. Okay, let's say u equal to 1.5, and then you let y1, y2 equal to 1/4. So if you y1 plus y2 over 1/4 plus 1/4, you get half, and half is 0.5, which is less than 1.5, isn't it? So that's why if you look figure, if you have 1.4, 1.4, which is 0.25, it will be here. So it will be below this line. Okay, u is less than u. Okay, all right. So y1, y2 satisfied the inequality of this one. Okay, what I mentioned just now. So therefore, y1 equal to y2, which is 1 over 4, falls in the shaded region below. This is what I say just now lah. Okay, you can see here the value of y1 and y2. All right. So similarly, all points such that y1 plus y2 less u lie below the line y1 plus y2 equal with u. So therefore, you will get the density, the distribution function of fu will be like this. Remember, we have this this step, and then you substitute u. Your u just now is u equal with y1 plus y2. So you substitute here, then you get this one. So basically, you need to integrate with respect to y1, y2, for the density function of this one. All right, so we check first when u is less than 0. That's mean if u negative value, so you will have this one. Okay, and it will get 0 as well, 0. So when you integrate 0, you get 0 for fu. Okay, when u is greater than 2, because just now we use u is 1.5, isn't it? So let's say u is equal with 2 or greater than 2. Okay, you can see that you have this one, you still have this one, but then it will be 0, 1, 0, 1. Okay, because we have the limit, and then you have here the density function, the joint density function is 1. So when you integrate 1, you get y1, and then you substitute the value, you get 1, and then you integrate y2, you get y2, and then you substitute the value, you get 1. Okay, if you remember lah, this one actually if you integrate the first one, you get y1, isn't it? Get 0, 1, and then the y2, and then when you integrate this one, so this one you have 1. Okay, and then here is the y2. When you integrate 1 with respect, you get y2, so 0, 1. So finally you get 1. Okay, so this is the distribution function, but now we want to see in between the value that we mentioned just now. All right, so for u is between 0 and 2. Okay, the limit of integration depend upon the particular value of u. Okay, because where u is the y2 intercept of the line y1 plus y2. So mathematically expression for the distribution function of u changes depending on whether u is between 0, 1 or u between 1 and 2. Okay, so we look one by one. So if u is between 0 and 1, the region y1 plus y2 is shaded area in figure 6.4. So you can see here, if we have y1 plus y2 and then the region is between 0 and 1, right? So this is the shaded area that we have. Okay, that's mean for y1 we have from 0 until this line, and then for y2 also we have 0 until this line. Okay, all right. Then for u between 0 and 1, we will have the distribution function like this. Okay, because we have the same thing, this is the density function, but the limit too, you must understand, because just now in the figure you have this square. Okay, you have y1, y2, here is 0, 1, 0, 1, but then you can see y1 plus y2 is here. Okay, so this is the shaded area. All right, so 0 until here. So how you get this one? Actually, you will have y1 plus y2 equal to u. So you can see that if you want y1, okay, if you want y1, you get u minus y2. So you have this limit. Okay, if you want this here, the limit, it will be from 0 until u. Okay, all right. So now you integrate this one. Okay, you will get this answer. Okay, this is integration as usual, and then you get this answer. Okay, and then you integrate with respect to y2, you substitute the value, then you get this one, u2 u square over 2. Okay, so the solution for distribution function u for limit 0 until 1, okay, could have been acquired directly by using elementary geometric, by this one lah. Okay, the bivariate density for y1, y2 equal is 1 is uniform over the unit square. Okay, because we have 0, 1, 0, 1. Okay, hence the distribution function of u is the volume of solid with height equal to y1, y2 equal with 1. And triangular cross section has shown in figure 6.4. Hence, your FU will have area of triangle times height. You get u square over 2. You get times with 1. Then you have the same thing, u square over 2. Okay, that one actually, this one, if I draw it 3D, okay, you have y1. So actually you have here 1, isn't it? Here is 1, here is 1, here is 0. So basically you have, okay, this one is not a nice angle. So let me show you. So basically you have this one. Okay, so here is y1, y2. So here is 1, here is 1. So yes, so you will get square solid volume. All right, but then when we put in a 2D, you can see lah, here is the value. Okay, here. All right. Okay, the distribution function can be acquired in similar manner when u is defined over the interval u between 1 and 2. Okay, although the geometric solution is easier, we will obtain FU directly by integration. So the region U, the region this one, and U between 1 and 2 is shaded area indicate in figure 6.5. So you have this one. Okay, the same thing lah. Okay, the same thing, but now instead of here, it will be at the above area. All right, so now the complement of the event U in the event y1, y2 falls in the region. Okay, so in this case, you can see that as A of figure 6.5, oh sorry, this one, okay, A is figure 6.5. Then for u is between 1 and 2, it will be 1 minus. Okay, because previously we found the area below here, but now it's up here. Okay, it will be 1 minus. Okay, 1 minus the bivariate density function for y1, y2. All right, so here again the limit you get from this one, y1 plus y2 equal to u. All right, but here it will be until 1 lah, because it's from here to there, here to there. That means from here to 1, and from here to 1, and from here to 1. So that's why the limits will be until 1, but this one, how you get it? It's from here. Okay, so integrate as usual, substitute the value, then you get this answer. Okay, so now this is the summarize. Okay, that's mean the distribution function of u equal with y1 plus y2. Okay, for u less than 0, you get 0. For u greater than 2, you get 1. For u greater between 0 and 1, you get this one, integration direct. But when you have u between 1 and 2, it will be 1 minus something, the other area. Okay, because you have 1 between u is between 1 and 2, so you get this one. So this is the total of distribution function of u. Okay, so it can be seen in shown figure 6.6a, this one. Okay, so basically at the moment for y1 and y2, you have until here, isn't it? Okay, but then when we have u is between 1 and 2, it become like this. Okay, all right, now that's the distribution function. In order for you to get the density function, you just differentiate this one. You differentiate the distribution function. Okay, then you just substitute the value, then you get 0 u, and this one 2 minus u, and then you get 0 for all this kind of limit. Or you can make it simplified. For u between 0 and 1, you get u. U between 1 and 2, you get 2 minus u, and then 0 otherwise. So a graph of the density function is shown in here. All right, this example quite complicated, but I think you can try, exercise, and look either you understand or not. Okay, so I think that's all for this video. Thank you, class.